So step 1 and step 3 is not too bad. Again, we'll talk about more examples on step 3. It's pretty straightforward. Just copy and paste pretty much the claim itself. But what the most important thing you're going to do when it comes to step 2 is the longest portion you're going to be seeing is step 2. Step 2 is the lengthiest of the hypothesis test, and it's the actual nitty-gritty stuff itself. Okay. The good thing is in step 2, we're going to break it down into 2 subparts. Okay. So before we actually get there, there's a couple things I want to talk about errors. So right, like this, because we're dealing with stats, there's always errors. Right. So there's 2 different types of errors when it comes to stats. The first one is called a type 1 error, or an alpha. Now, we talked about alpha before, right? So same type of alpha. It is same concept. Now we just brought it more an example. It's the mistake of rejecting the null hypothesis when it's actually true. Okay. So a type 1 error is called an alpha error. And a type 2 error is the mistake of not rejecting null hypothesis when it's actually false. So let me give an example of what a type 1 error is all about. So again, type 1 error is the mistake of rejecting the null hypothesis when it is actually true. So let's suppose you're on trial for stealing something, okay? And so you're actually innocent, right? So you did not actually steal this object, but you're on trial for it, and the judge finds you guilty, right? So they find the alternative is actually true when the null hypothesis is actually true. So you were actually innocent, but they got you guilty on this concept. That's what's called a type 1 error. So that's the main error we're going to focus on here. A type 2 error is, we're not actually going to calculate that. That's in higher stats. But it's just the opposite of it when you actually stole the item. However, the judge says you didn't steal it when it comes to it, right? So you actually got double good, right? You stole it and you get off not guilty. This one says you didn't do it, but you got guilty for it, which, it's a big no-no, right? That's a huge system when it comes to it. So that's what's called a type 1 error. That's one of the most important things when it comes to this type of stuff for our case, okay? So now we're going to talk about type 1 errors a little bit more in detail, okay? So this is called also a level of significance, okay? So this is the probability of making a type 1 error, right? So we want that error to be super, super small because, it could be life and death situations, especially if you go to, like I said, in the judges systems, right? You can go for, long time in prisons for little errors when it comes to it. So for example, a significance level of 0.05 indicates a 5% risk of concluding that a difference exists when there's no actual difference. Okay, so again, like I said, right, there's a 5% error when it came to my example of you being guilty when you actually, didn't do it as well, right? You made a huge power, that's a big percent, right? 5% when it comes to, going to, prison or not. But, we always usually want that error to be super, super small when it comes to it. So most of the time when you do this in the judicial system, and you'll see later on in examples, is it's less than 1% chance because, it's in the hands of a lot of people when it comes to it. And hence the reason why a lot of times they go into juries, right? Not just one person when it comes to it. But we'll talk about that more in a little detail. All right, so before we get any further, we want to talk about, there's 3 different types of tests we can deal with, okay? And this all corresponds back to the alternative hypothesis. So what is being less than, greater than, and then not equal to, okay? So we're always looking at that. So let's look at, so if we have that the parameter is greater than the value. So for instance, example 2 here, right? No, the alternative hypothesis P is greater than 10.5%. Okay. So if we have this happening, this is what's called a right tail test. And the reason why it's called a right tail test is we're actually shading the right side of the tail. That's the reason why. That's it. That's why it's called the right. And if it's easy to identify, you can just say, well, which way is the arrow pointing? It's pointing to the right, hence it's why I call it a right tail test. So therefore, you could probably figure out what's going to be 2 since it's arrow pointing to the left. This is called a left tail test. Which means when we do our curve, we're going to be shading the left-hand side of it. And now when we have not equal to, this corresponds to something called a two-tail test. What that means is we're going to shade both ends of the tails. Which makes sense because I don't know if it's bigger or less than, right? I don't care which it is, but it's not equal to that certain value. Hence why it's called a two-tail test. Things like that. Okay. So we have right-tailed, left-tailed, two-tailed, and it all goes back to the alternative, right? That's what we see. We look at the alternative hypothesis and see from there, do we have right, left, or two-tailed based on, literally just the sign, right, where it's going to. That's all you're really looking at for the alternative hypothesis, okay? Right, so now let's go to the next part of the step 2, okay? Now, when it comes to us, because it's pretty difficult using a calculator, we're actually going to skip here. So we're not going to do the p-value method. We're going to straight use something called the classical approach, make it easier for you guys to deal with, okay? So this is the analyzing portion. So if you go back over here, the test that's the most difficult to find. The analyzing stuff is actually much easier. And this is the first step of analyzing, finding what type of test we have first, and then from there, using these two types. And again, this is preferred mostly when you go into actual programming stuff, but it's using a calculator. But for our class, it's probably easier just to figure out using the classical approach, makes it much easier to deal with, okay? Since we're having the tables anyways. So when we do the classical or / traditional method, what we want to do is we want to test it. Is it going to be, do we reject or do not reject? Like, in other words, which one's going to be true? Is, after we do all this test, is this true or is that true, right? We got to figure out which one it is. And that's what we're going to be dealing with here, right? So first thing is we want to define something called a critical value. So is a value that separates the critical region. The critical region is the area of alpha for a given test. So in other words, if we go back over here, these shaded regions are the critical regions. So these are the alphas themselves, each individual case. So the alphas are going to be the level of significance, right? That 5% error, or roughly what is given to us in each individual question, okay? Those are the alphas respectively going to be, because that's what that means here. Okay? So once we find that critical region, or that separates it, the critical value, we're going to have one of these happening. So we say if the test statistic is in the region, then we reject null hypothesis, which means if we reject it, therefore there is evidence to conclude that this is actually true. However, if the test statistic is not in the critical region, we do not reject the null hypothesis, which means this was true to begin with and as we started with, which means there's not enough evidence to state that this is actually true. Okay, so that's to mean that just shows you which one is actually going to be true based off this information. Okay, so here's a little example illustrating how to find the critical values based on this. So example 2 says, suppose we have a right-tailed test. So here we go, right? A right-tailed test means you're shading everything on the right-hand side, so all of this. And the test statistic is z equals 2.32, and alpha is equal to 0.05. Find the critical region and the value. Now, this is the best part. When it comes to z-scores, right, we're using normal distributions, right? So quick little fact, right? Z-scores are normal, t-values are t-values, cubes, and chi-squared values are going to be, the actual chi-squared values, right? So we have to do those. Now, if you guys go back to your formula sheet, if you guys go way down at the very bottom, hopefully you guys see this. Let me see a closer. See this? Look at that. When it comes to proportions, whenever we're doing proportions, so for example, question 2 in the last examples, right, coming proportions, you already have the critical values done for you right here. All you have to do is identify what type of test we have and what is the alpha given to us in the question. So for example, in our case, our alpha was 0.05. Wait, where's my 0.05? And we had a right tail test, so which means our critical value is 1.645. And that is how we get the number at the bottom of your portion, 1.645. So this right here is a shaded region. So now we want to figure out is, okay, again, right, it's a marker. So our z-score is 2.38, or 2.22, which is roughly here, right, approximately there. Now here's a question for you guys. Is our test stat, so this number right here, in the shaded region? And hopefully you guys say yes, right? Okay, so since you guys say yes, therefore, which one of these are we in? Question, step 1 or step 2? Hopefully you say step 1, right? Since it's a yes, it's in the critical region, so therefore we reject the null hypothesis. That's how we're going to figure out if we say reject or not based off that information. Okay? And again, it just shows you right here everything I just talked about, how to find that portion, right? It comes with, so again, since you're right, 2.7 is in the region, therefore we reject the null hypothesis. So therefore, the alternative is actually true based off that information. Okay? So don't worry, there's a couple more examples we can deal with when things like that, because then, I don't want you guys just go completely off. Now, let's go to example 3. So let's suppose we have a situation of this. So here's a situation, right? This is our null hypothesis, and here's our alternative hypothesis, right? So, fun fact, what type of test do we have? Hopefully you guys said two-tailed, right? Because it's not equal to. So we have a two-tailed test based off this, right? So we have a two-tailed test automatically, and they also give us alpha. And we have a test set of 1.85. All right, so the question is, right, we want to see if we reject or do not reject based off this information. Okay. Now the cool thing about this is because we're going z's, we can just go back over here. We have an alpha 0.05, which is right there. We said it was a two-tailed test, so two-tailed. So notice now we have plus or minus, right? Because we have the left side, also the right-hand side. So therefore, we have positive 1.96 and negative 1.96. And that's how we get these values here. So these are shaded regions because it's a two-tailed test. Okay. And again, we do the same thing. So our z-score is over here. Let's see, 1.85. Again, the question is our test that, right, the test that we have here, in the shaded regions? And hopefully you say no, right? Okay. So because they're not, which means now, we go back over here, now we're in situation 2. Therefore, since it's not in the region, we do not reject the null hypothesis. And that's it. That's how we do that portion. So z-scores are very nice. We'll talk about z-scores right now so you can see how that corresponds to t-values. But z-scores are really nice because, again, the table is already here for you. Now, for your sake, right, I'm going to help you guys out. I'm always going to give you these type of values. I'm not going to change it for you guys, okay? So you can always use these three because they're the main ones you're going to be seeing in real life anyways. So, those 3 types will help you out when it comes to it. All you have to do is remember it's in your z-score tables, okay? All right, so the next video we'll talk about example 4 and move on from the section as well.